Let's look at number 5. Says the following data was acquired in an iodination experiment involving acetone. All reaction times are in terms of the rate of disappearance of slash RMI2. So I guess it's I2. Trial I2, and you get some type of data here. So it's actually a really bad formatting, so I really don't know what we're looking at here. But it's saying rate E is equal to the constant times I2 multiplied by H plus divided by there's a rate law here. So let me write the rate law here. And it says it's asking us what is the values of x, y, and z. Okay, so you want to find the exponents in the rate law here. So I have I2 x, and then I have H plus y, and then finally CH3 CO CH3 Z. And I want to figure out x, y, and z. So in order for us to do that, we actually divide out the exponents here. We keep one of these guys constant, and then we would divide out another reaction. And the reason why we do this is if I were to divide K and then by I2, if we know one of these values here, and I keep these two constant, then I can figure out the concentration of one of these, the CH3CO CH3, and if I divide it out, I can actually get, I can algebraically isolate for those guys here. So I would basically divide everything by a constant set of values, depending on how they have the data set up here. So I don't know if they actually figured out the data here, but I guess I don't know if it was in a chart or something like that, but that's how you would go about this question. So let me see what they're doing here. So rate equals negative I2 over delta T. So I think are given time as well. I don't know from this chart. If you're given time, then you can also use the other formula where it says rate equals negative the concentration of I. The change in concentration of I2 divided by delta T here. That also works as well. So let's see. So for experiment 1, they had M1 and V1. So they're solving for concentration 2, which is I2, to figure out the rate here. So they got this rate, which is 7.9692 times 10 to the negative 7. And then we get another rate here, which is for experiment 2. So the rates would cancel out. So you would be able to figure out the concentration of iodine, which is 0. So X here would be 0. And then basically you repeat the same step for Y and Z here. So let me break this down for you, and we can figure this out together. And I'll only do one iteration of this because it's the same iteration for Y and Z as well. So through the data that's, I guess, given here that I definitely can't see, they figured out that concentration is equal to 0.1 and the volume is equal to 5 milliliters. So we're going to use C1V1 equals C2V2 to figure out the concentration of the second of M2, which is I2. So in this case here, they got this is equal to I2 is equal to 1 times 10 to the negative 4. And then we have our concentration, which is 0.01. So we subtract both of those guys and we divide it by delta T, which is going to be 130 seconds in this case here. And again, this should have been given in the data, but it's not. So I'm kind of going off whatever these guys are writing here. And then I get some type of rate here. So rate would be equal to 7.692 times 10 to the negative 7 moles per second. And as for experiment 1, we do the exact same thing for experiment 2, where we get, again, we have 0.01, and in this case now we have the second volume, which is 10 milliliters. Our V2 is the total volume, and we're solving for C2 here. And again, C2, we found that it's going to be equal to 2 times 10 to the negative 4, and we divide those out here, and T, in this case here, is 249 seconds for experiment 2, and this is going to give us another rate, which is 8.03 times 10 to the negative 7 moles per second. And assuming that this has been done in the lab, we can safely say that these two are very, very similar to each other. So therefore, the rates are going to cancel out, and we've simply just doubled our the concentration of iodine here, right? So we have let's see here. So we doubled our concentration of I2, but the rate was still the same. So therefore, the I2 is going to be a 0 order reaction. So this is a 0. So therefore, we can say that x here is equal to 0. So x equals 0. And basically, you do the same thing for y and z here. So they did the same process for iodine. So you got the rate for experiment 3, 4, and 5, and then you compare the rates together, right? So you see that this is 1.6 times 10 to the negative 6. This one's also very, very much the same, and this one is 5.37 times 10 to the negative 6. And you're comparing H plus instead, right? So you're comparing the concentration of H plus in experiments 2 and 3. You figure out that they double, but the rates, let's see, the concentration of H plus is doubled, but the rate is also doubled, right? So therefore, you have a constant rate here. So if I'm doubling the concentration, I'm doubling the rate as well. So y, you can say y would equal 1 because it's a first order reaction. And then similarly for CH3COH here, you can do the exact same thing. You have experiment 1 and 2, and then you can divide out the rate here, and you can figure out the concentration of that. So let's see here. They solved for activation energy. I don't know why they did that. I think they're just solving for x, y, and z here, so that's probably not good here. But they did solve for experiment 1. They did solve for the rate here, and so it says here. So in order with respect to acetone is equal to 1 as rate doubles when acetone doubles. So therefore, z here is equal to 1 as well. So this is the first order. So overall, the reaction is in the second order. However, x here is 0, y is equal to 1, and z here equals 1 as well. Because again, for 0 order, even if you double the concentration, the rate still stays the same. In the first order, if you double the concentration, the rate also doubles. And then in the if we had a second order reaction, if we double the concentration, the rate would actually quadruple, so it would be 2 squared. So that's how you would solve for this problem here. So I'm going to say solution is correct. And then just say x here would equal 0, y is equal to 1, and z is also equal to 1. Data table was not shown correctly due to formatting. The solution here is correct.